Well, thank you very much for the invitation. It's an honor to give these talks. My first talk will be a colloquium style talk and will be about Syzygies of algebraic varieties. Now, algebraic geometers study algebraic varieties, and algebraic varieties are precisely the geometric object defined by polynomial equations. So it's very natural to study the relation among these equations, or maybe relation about this equation. And these are the so-called syzygies of the varieties. Now, to be honest, the topic of syzygy as is the same for a talk is really too wide, and it involves too many topics. And so the purpose of this talk would be somewhat much more narrow. It's still a survey talk, but it's somewhat biased in the sense that I will only think that I have studied myself. And unfortunately, I mean, this gives a somewhat biased picture, and it's also I had to miss out a lot of very many important topics, and so I apologize for that. I should also say that many of the results that I report on are joint work with Robert Leisesfeld. And now, so let me talk about this. So I consider polynomial ring. Let me just work over the complex numbers, even though most of the talk actually work for any algebraically closed field, or even for any arbitrary field. But let me just, for simplicity, I just work over the complex numbers. So this is a polynomial ring of R plus one variable. We will regard this as a graded ring. That means I write the polynomial ring S as direct sum of Sj. Sj are just precisely the set of all the homogeneous polynomial of degree j. And we observe that it has the property that Si times Sj would be Si plus j. And in here, there is a unique maximal homogeneous ideal that is the summation of the Sj for j greater than 0. That is the unique, basically all the positive degree polynomial, homogeneous polynomial, and the span. And the quotient is just simply isomorphic to S0, which is just the complex numbers. And now, in general, we're looking at some finally generated graded S module. What that means is just simply E is equal to direct sum of EI, and it's the S module in the greater sense that the degree j part of S times the degree I part of E will land you in the degree I plus j part of E. Yeah. Now we want to talk about generators and relation on E. So suppose we choose a set of generator M1 to MB, and let's say they are homogeneous of degree A0j. This amount to a sum from the free module S minus A0j to E, where the sending some tuple F1 to FB to summation Fi Mi. And well, here the notation S of j, a so-called the twisting of S, is basically just a graded S module, but just with a different grading. The degree I part of Sj twisted of degree I part is precisely the S of I plus j part of the original polynomial in S. Now we have the map epsilon that map onto E, and then you look at the kernel of this, and I can think of epsilon at delta naught also, and then you choose a generator of the kernel of epsilon or kernel of delta naught, and then you choose generator of this, and we can keep on doing this, yeah, choosing homogeneous vector. And then what you will find would be a free resolution of the module E. Now, one want to do this efficiently, then use minimal generators. And so we will do that, and then look at the kernel of delta naught after you choose minimal generators again. And in this fashion, what you get is getting something called what we call a minimal graded free resolution of the module E. And now the graded version of the Nekiyama lemma will say that a finitely generated module over S, graded module over S is equal to 0 if and only if its tensor product with the residual field C is equal to 0. So a map epsilon naught is surjective if and only if epsilon tensor C is surjective, therefore. And to choosing minimal generator, it's just corresponding to choosing epsilon such that the map from P naught tensor C to E tensor C is precise isomorphism of graded vector space. And now since the P dot is a presentation, so you see that this is also equivalent to saying that the map delta 1 as tensor C is equal to 0. And this is just simply equivalent to saying that if you look at the matrix representation of delta 1, then all the entries of this matrix are in the maximal ideal M. Okay. So in general, a minimal graded free resolution, you just have the property that the delta I tensor C are all equal to 0 for each I positive. Okay. Now, the so-called Hilbert-Syzygies theorem, that is the first basic theorem about Syzygies, and it says the following: the minimal graded free resolution E is unique up to isomorphism. Furthermore, the length of the minimal resolution is at most R plus 1. Recall that R plus 1 is the number of variables of this polynomial ring. And the proof is, using from modern point of view, is not hard. Yeah, you tensor this complex with C, and now the homology of this complex now is just by definition of tau. Remember, tau is just simply resolve the module E, and you compute its tensor product with C, and then compute the homology of precisely the tau group. The homology, therefore, are just simply the I homology is just simply tau I of CE. And now, because all the boundary map are 0, because we have a great minimal resolution, and so therefore, in fact, the tau I of CE is just isomorphic to PI tensor C. Now, tau is a bifunctor, so you can compute the tau group either by resolving E or can resolving by C. Now, the C has a nice Kouzou resolution of length R plus 1, and from that one can see that the length of the resolution is most R plus 1, because the length of resolution of C is only of length R plus 1. Now, the basic invariant of this minimal resolution are the Betti numbers, and the Betti numbers, you see, you can think of the PI are just simply from this identification, basically it's just simply the tau I of CE tensor with S. Think of tau I of CE as a graded vector space. And the Bij, this is the so-called Betti number of the minimal free resolution, is just simply the dimension of the graded vector space, tau I of CE, the degree J part of that. That would be the Bij. So the invariant of this complex, the basic invariant of this complex are precisely these Betti numbers. Now, we can describe this more precisely using what we just said. The tau group can be computed using the resolution of C, which is just simply Kouzou resolution. You just simply sending V to be the degree 1 part of S, that's the summation C of xi, that map onto the maximal ideal M by sending the generator to xi. And then the tau group are just simply given by wedge I of V tensor E of J minus I, and then map to the each graded pieces, and the homology of this complex that are written down at the bottom row of this page are precisely the tau group. And the dimension of this tau group are precisely the Betti numbers. Now, the basic question is the following. So suppose the module is the ideal of some homogeneous variety. Yeah, it's given by some homogeneous ideal. It's of some projective variety X. The one asks, basically, if we study the syzygy or study the resolution, what can one learn about the geometry of X from the syzygy or from the minimal resolution of E? So this is the kind of question one would like to know. And another thing you would like to know is, for instance, can one use the resolution in some sense? If you want to input the information about the variety into the computer, then you just have to input the complex. The complex are just given by basically all this boundary map delta I. Those are just some matrices with polynomial entries, so that it's pretty convenient to enter into the computer. And you can ask, how complicated is it to compute this minimal resolutions? So a basic invariant is called the Casanova-Mumford regularity of E, which is weaker and hence a much more accessible invariant of the grading of the P dot. Instead of Betti number, one asks a slightly simpler question. The regularity of E is just defined to be maximum of all the j minus I, so the Bij of E is not equal to 0. Now, in the concrete term, to say the regularity of E is less than equal to M, that means the following. The E is generated by generators in degree less than equal to M. The ICCG module, remember the ICCG module is just simply the kernel of the delta I, and they are just generated by all the elements of degree at most I plus M. So it's just tell you, the regularity roughly tell you how far you have to search before you can find all the syzygies. And the regularity tell you that a bound in how complicated it is to find the syzygies. Maybe the simplest example is the so-called twisted cubic curve. And the twisted cubic curve is given by a projective embedding of CP1 into P3, taking the projective coordinate ST into SQ, S squared T, ST squared, and TQ. And now the homogeneous ideal, the resolution will be of the following form. Is 2 generators, should be 3 generators here. That's print. That should be 3 here. And given by 3 quadrics, and there are 2 linear relations among the 3 quadrics. And the map delta 1 are given by the simple matrix, and the epsilon, the map of to find the generator. All you need to do is just simply find it. All the 2 by 2 minus will be given sign, such that the of this matrix delta 1. And then for instance, in this example, you see that the regularity of the twisted cubic curve is precisely 2. And more generally, you can see that, for instance, if you have X is a variety of minimal degree, then the regularity of Ix is equal to 2. Conversely, if you assume X is a non-degenerate variety of codimension E, the minimal variety of minimal degree just simply means that this variety has degree E plus 1. And this you can easily show that this is really the minimal possible degree of something of codimension E. And non-degenerate just simply means that the variety X is not contained in the hyperplane. So if it's contained in the hyperplane, then it's already naturally embedded into PR minus 1. So we may replace R by R minus 1 doing the calculations. All right. So here you see that, again, the regularity is small, like 2. Then in some sense, it's also corresponding to the simplest variety. In this case, they are precisely all the variety of minimal degrees. Now, Mumford interpretation of the regularity is one of the, in terms of shift cohomology, is the following. To say that the homogeneous ideal, Ix has regularity less than equal to M. And that is equivalent to saying that the map from X naught PR m minus 1 to not OX of m minus 1 is surjective, and the HIOX of m minus 1 minus I is bigger than equal to 0 for all I positive. And this is equivalent to saying that the ideal sheaf satisfies the following vanishing theorem. And it's just simply saying that HI of the IX, where this IX here is the ideal sheaf of X inside PR, satisfy the vanishing theorem that when you choose it by m minus I is equal to 0 for each I that is positive. Now, a long-standing a conjecture by Eisenberg and Gordo say the following. Well, you say that, well, the regularity of IX is bounded in a very simple manner by the degree of X and the codimension of X. So in this case, the conjecture actually predicts that regularity of IX is equal to less than or equal to D minus E plus 1. And for instance, if X is a variety of minimal degree, you can see that this is this inequality is an equality. Now, if X is non-reduced, if the scheme OX, the structure sheet OX has nilpotent, then this is far from being true. And the example due to Meyer and Meyer show that there are doubly exponential growth of the regularity in terms of the degree. Yeah. And maybe the first basic theorem along the conjecture is the theorem of Gruson, Laissesfeld, and Pasquin. You say that the theorem is true, the conjecture is true when X is a curve. And then become the work of Laissesfeld on dimension 2. He proved that the conjecture is true for smooth projective surface, and that refining the earlier work due to Henry Pinker. And for dimension 3 and dimension 4, there's work by Sifran and Xijun Kwak that the conjecture is almost true, is off by a little bit when X is either a smooth 3-fold or smooth 4-fold. And in 2017, the McCullough and Peever basically using something called the Riesz algebra. Riesz algebra is just what the algebraic geometry called the blowing up algebra. So they used one note that for any arbitrary ideal in the polynomial ring, for instance, if the scheme defined is as a lot nilpotent, then the regularity can be very complicated, for instance, by the Meyer and Meyer examples. But if you look at the Riesz algebra, is just a measure direction IX to the M, then that the Riesz algebra itself is an integral domain. So you do get a sort of something looks like a variety. And what McCullough Peever does is that what they did is somehow modify this Riesz algebra in a way such that it becomes a projective variety inside projective space in a fashion they can still control the complexity of the computation of the regularity. And in particular, what they show is that the conjecture itself is false if you're just assuming X is irreducible reduced and for dimension greater equal to 4, and more recent work of Hahn and Kwak show that in fact they're already counterexample for singular surfaces. So really, if you allow singular surfaces, I think it's just the singularity is just too complicated and it's hard to control the regularities. Now, there are other progresses. So for instance, instead of the regularity of the ideal sheaf, one can look at the regularity of OX and their work of Jin-Young Park and Kwak that saying that actually one can bound the regularity by D minus E. And in fact, they did a lot more. They classified the boundary example, maybe even a boundary example -1. Now, let me just mention These are the result. This is all result of myself, Edward Bertram, and Liza cell. So this is the setup. So instead of inputting the complexity of the degree of the variety, I mean, you can sort of suppose you're giving a bunch of equations that defining the projective variety X inside PR. So you're given by a bunch of equations, yeah. And let's say they are defined by they define hypersurface of degree D1 up to Dm, and let order them such that D1 is greater equal to D2 up to Dm. Then the theorem that we proved is the following, that the regularity of Ix is bounded by D1 plus D2 up to dE, where E is a codimension minus E plus 1. And furthermore, the result is the boundary example where the regularity, the inequality of the regularity is equality if and only if the X itself is a complete intersection of type D1 to dE. And now one may ask why this only involves the first E number. So the following is roughly the idea. So instead you look at the blowing up of P. This is the blowing up of X along the PR, yeah. And here you have the exceptional divisor. And this is inverse of X. And the classical thing to do is the following. You take a bunch of hypersurface of degree D1 to dE. That's the general inside the ideal generated by the Fi. And so you look at this will form a complete intersection, again, of codimension E that containing X. So the complete intersection split into two parts, X and X prime. And this X prime is called the residual part of X with respect to this complete intersections. And now in general, downstairs in PR, that this residual scheme in general will be singular. But fortunately, on the blowing up, you sacrifice by working on a slightly more complicated space. Then the residual part will define something, in fact, something smooth. And turned out the theorem just follow from Kodala type vanishing theorem apply onto this residual part, and using that the push forwards O minus E is just equal to the ideal shift downstairs. So it's not something very complicated at all. So the observation here is F low star O of P prime minus E is just equal to Ix. And from that, using the Kodala type vanishing theorem, you can control the vanishing theorem of Ix and more general for the power of Ix also. Now, the old observation of Mumford is that if you have a smooth projective variety of degree D, then already the scheme X is already cut out by surfaces of degree D. So you can choose a polynomial, the hypersurface Fi, to be all of degree D, and then you see that the regularity bound will be bounded by the minimum of E comma n plus 1 D minus E plus 1. So at least we get a linear bound for the regularity by this very simple method. Now, for lower dimension, most of the results one obtained are considered by so-called generic projections. And one understands the generic projection fairly well. One is low dimension, but the complexity will go up pretty quickly. So an observation of Liza cell is that the following. And if you look at the maximal length of when you take a generic projection, you look. So the map from X, you take X map to a hypersurface in Pn plus 1, and you get a singular hypersurface. And But the fiber can get more complicated. The length of the fiber of such a generic projection, if you're taking the possible maximal length, the thing does grow exponentially with respect to maybe the square root of the dimension or something like that. So, with some new idea, again, this seems to be still a very interesting question, and it's an open question, and one would like to hope that in the future one can make more progress on this question. I mean, for instance, you can ask, instead of one generic projection, can you consider a family of projection and things of this type? And one can also ask, instead of the length of the fiber, can one look at, this is the idea of Behesty and Eisenbart, is that instead of looking at the length of the fiber, then one can ask whether one can control the regularity of the ideal shift of the fiber, things of this type. And if one can make progress on some of these questions, then I would expect that one would be able to make more progresses on this type of conjecture. I mean, I think it still remains a really reasonable conjecture if you assume X is smooth instead of arbitrary, irreducible, reduced variety. I think singularity does contribute a great deal to the complexity. Right? Now, property NK. Now, that X be a projective variety, and L is a very ample line bundle. Then one can consider the so-called abstract coordinate ring of X comma L. That is a simply direct sum of X naught L tends to M for all positive power, negative power M. And this is called the abstract coordinate ring for the pair XL. Now, it's obviously a module of the polynomial ring symmetric algebra of, and then one can consider the minimum modulo R as an S module, just like what we did before. And this define the KPQ, also through the Kosciuszko homology, to be the tau P of S of RCP plus Q. And so the shift that it's just, because the boundary map all have degree 1, so the general, to see if you're something is general by all degree D thing, then the relation has to be at least of degree D plus 1. The shifting is just simply making a count of this shifting that on degree, make it more convenient to work. So the N0 it just simply means that the natural map from S go to R by setting 1-to-1 is surjective. So basically saying that the module R is generated by a single generator given by the natural, the element 1 in degree 0. And for each K positive to say L is satisfied by NK, if it's satisfied N0, and together with the vanishing of the KP group, Q group, and in this range. And I mean, more concretely, you just simply say the following. So NK property is just simply say, if you look at the first K step of the resolution, so of this abstract coordinate ring, the first step is just a copy of S. And the next one will be just sum of S minus 2, is just simply saying that homogeneous ideal of X in the embedding given by the complete linear system L is generated by quadrics. And the next map, then the delta 2 are given by linear form, saying that all the relation among the quadric Qi is given by things of the form summation Li Qi equal to 0. Yeah, and etc. So for the first case step. Now, the first case to consider is the case that X is a smooth projective curve of genus G, or a compact Riemann surface of genus G. And now C is called hyperelliptic if there is a 2-to-1 map from C to P1. So for the talk today, I would always assume C is a non-hyperelliptic curve. So assume that it the curve is not a 2-to-1 mapping to P1. If it's a 2-to-1 mapping to P1, then you ramify in certain number of points, and one can construct the curve very explicitly. So in that case, one understands the geometry of the curve very, very well already. So I may just let me assume that the thing is not a hyperelliptic curve. In that case, the curve can be embedded by the complete linear system KC. The canonical divisor is simply the cotangent bundle of C. Yeah, C is a curve, so omega C is a line bundle. And in this case, the line bundle KC is very ample. That means that the mapping here is embedding. Now, so because the canonical bundle is canonical, so one would expect that one can relate the geometry of C to the projective geometry of the canonical curve. The canonical curve is the embedding of this curve into PG-1 under the complete linear system KC. And so maybe the first thing is a so-called geometric Riemann-Roch theorem. Yeah, you simply talk about the following. Suppose you have a divisor. If you want to just think of being these distinct points, yeah, then you look at the span of these distinct points. That would be a linear space inside PG-1. And they're called a D bar. And the geometric Riemann-Roch is just simply say that this number is equal to D minus H0 of OC of D. And this is a follow from the classical Riemann-Roch. Classical Riemann-Roch together with their duality basically gives you the formula H0 KC minus D equal to H0 of D plus G minus 1. And minus D, and then once compute them, once the codimension of D is just equal to H of KC minus D, and the simple calculation say that the dimension of D bar is just what we said is the D minus H0 of D. So a simple example would be the following. Suppose the C is the next case, the most simple thing would be C is a trigonal curve. What that means is that C is not hyperelliptic, and C has a 3-to-1 mapping to P1. And you look at the inverse image of a general point Q, then that would be the inverse image would be 3 points. And then you compute that the span of the 3 points, that would be by the formula of the geometric Riemann-Roch is 3 minus 2, so it's 1. So the span of this 3 point is a line L, and this line L will intersect the curve at the 3 points. So what you see is that the curve possesses a trisecant line. Now, geometrically, this already tells you that it prevents you from saying that the homogeneous ideal to be generated by quadratic, because any quadratic hypersurface containing C, then this quadratic will intersect the line at least 3 points. But a quadratic form on P1 can only, if a non-zero quadratic form can only vanish at 2 points. So that means the restriction of this quadratic form to P1 has to be 0. That means geometrically just simply say the quadratic hypersurface must contain the line. So the degree 2 part of the homogeneous ideal, all this intersection of this hypersurface will contain both C and the line L. So now, this is basically the classical theorem of Noether and Petri, saying that if C is a non-hyperelliptic curve, then KC satisfies N0. So that means the natural map of the polynomial ring to the abstract coordinate ring is surjective. And Petri is saying that the homogeneous ideal is generated by quadratic. That means the N1 is just the sum of S minus Q. That just simply means that the curve is either trigonal, we see that trigonal is no good already, and or else it's a plane curve of degree 5. I leave it to you as an exercise to see the simple reason why that if it's a plane curve of degree 5, then the mapping into P5, the thing cannot be a cut out by quadratic. In fact, the intersection of the quadratic will be precisely the Veronese surface. In 1984, Green published his very influential paper on Kusuko homology. This paper brought a lot of new insight into study of syzygy. And for instance, he had this following thing, is saying that if the L is a line bundle, if the degree of L bigger than 2g plus k plus 1, then the L will satisfy nk. And this generalizes the classical result of Noether, saying that if d bigger than 2g plus 1, then L satisfies n naught. And the Fujita result saying that 2g bigger than 2g plus 2, then L satisfies n1. Now, to understand the green conjecture on canonical curve, one would first need to understand some invariant of the curve. The first thing is the so-called gonady of the curve. The gonady of the curve is simply the minimum of all the positive integers such that there exists a divisor of degree delta such that x naught OD is equal to 2. And equivalently is saying that there is a degree delta map and to P1, and delta is a minimum of such possible degree of such possible map. So this is just generalized the hyperelliptic curve and trigonal curve quite easily. And the next thing is slightly more complicated. It's the so-called Clifford index. So if A is a line bundle, then generalize the classical Clifford theorem, then you consider the expression degree of A minus 2 times x naught A minus 1. And by Riemann rock, you can see that this is equivalent to the following expression equal to g plus 1 minus x naught A minus x naught kc tensor A inverse. And one see that that is also equal to the Clifford of kc tensor A inverse. And the Clifford index is just defined to be minimum over all the Clifford index of A, such that both the A and K tensor A inverse to be non-trivial linear system, where both a linear system are greater than or equal to 2. Now, for instance, if you have Planck curve of degree phi, then x naught of the O of 1 of P2 residual the curve will give you a line bundle with 3 sections and degree of A is phi. One compute the Clifford index is 1. And similarly for the trigonal curve, one can also compute the Clifford index is 1. So one can check that basically Patrick theorem is equivalent to saying that the thing failed to have N1 even only if the curve had Clifford index 1. And basically you can check that the only thing with Clifford index 1 are just simply these 2 examples. Now, the green conjecture is just simply say the following, saying that the canonical curve satisfies property nk even only if the Clifford index is greater or equal to k. And the Patrick theorem is saying that conjecture is true for k equal to 1. And Poisson and Schreier proved that the conjecture is also true for k. And roughly like 10 years ago or something like that, and Poisson proved that using K3 surface and Hilbert scheme of points of K3 to show that if C is a very general curve, then the conjecture is true. It's a general curve, then this is true. Now, I would like to make a remark. You look at the minimal resolution of this abstract Gordon ring RC, and by duality, you see that the dual of this resolution of the twisted by minus g minus 1 is also be a resolution of RCKC. So basically P dot and P dot dual and minus g minus 1 is isomorphic. So what that say is that if you know the first half of the resolution, the duality will also determine the second half of the resolution. So basically, as long as you know the first half of the Syzygy, the Betti number, you would know the Syzygy of the second half also. I mean, let me just look at some quick example. There's a genus phi curve, which is a general curve. Such thing would be complete intersection of 3 particle Kousou complex. And you can see the duality here. You see the middle 2, this 3 and the 3 here, 1 and 1 here, the Betti numbers. And you can see the symmetry here. And in general, the duality, the Serre duality will tell you that the minimal resolution, saying that there's a symmetry between first half of the basically P and P dual up to twisting. A few years ago, then Prudu, Farkas, and Papadima, and Reiku, and Weisman proved that the using this representation theory and the tangent developable surface. So this is just simply the tangent union or the tangent line of a rational normal curve in PG. And it's known that such a thing is a degeneration of the K3 surface. And from that, basically they give another proof of Voisin's theorem that's saying that the general canonical curve will satisfy the green conjecture, and their proof will also work for characteristic P if P is sufficiently large. And more recently, Park has given a proof of this theorem by using not only just the tangent variety, but also the secant variety of the rational normal curve. And here also that Kemeny also give a new proof of Voisin theorem using rank 2 bundle on K3 surface. Maybe I should explain why K3 surface is coming in a fairly natural way. So first of all, if X is a K3, yeah. So that just means that it's a smooth projective surface. And such that is H1 of OX is equal to 0. And the canonical bundle, this is the second exterior product of omega X, is also trivial. And suppose X is a very ample divisor on X, the OX of H, and let's C to be an element in the linear system H, the OX of H restricted to C is just the canonical bundle. And basically, if you take a minimal resolution of the K3 surface with respect to the line bundle H, then it will restrict it to a minimal resolution of the canonical curve. So if you want to interested in computing the Betti number of the minimal resolution of the curve C, you can also computing it using the K3 surface instead. Now, so Leissenfeld proved the following. Leissenfeld said that if the Picard group of X is equal to C times H, so he used the to show that in this case that is this curve C you get will satisfy. He gave a new proof of the he proved that the Syzygies theorem, which is the theorem, is a conjecture of Petri that describe in a fairly complete way about line bundle and linear system on a general curve. And so basically what Leissenfeld theorem say is that if you take any C such smooth curve on a K3 surface with the Picard group rank is 1, the curve behaves like a general curve. But in general, it's hard to put your hand on a general curve. And what this is give you a very concrete way to study the general curve by studying curve on the K3 surface. And on the general curve, the Clifford index, let's say G equal to 2K or something like that. Let's say even. And the Clifford index of C in this case is under this assumption is one can see what is equal to G minus 1 over 2. That's true for general curve. And the Clifford index will be computed by a tensor. It's given by a line bundle of 2 sections. And let's say the line bundle is A. A is this section on C, such that X naught A equal to 2. Then you get an exact sequence of locally free sheaf on the K3 surface like this. A is on C. And if you take this dual, then you get 2O of X go to E equal to KC times A inverse. So what you find is the X naught of E of A is equal to X naught of A plus X naught of KC times A inverse. And we call the Griffith index of A is equal to G plus 1 minus this sum. So what happened here is that on the K-free surface, you combine basically saying that the Griffith index basically can be replaced by the number section of this vector bundle EA. And you would expect then the projected geometry of EA will tell you about the syzygy of the curve. And that is turned out to be indeed the case. So that is basically the philosophy why the K-free surface is a convenient thing to use to studying these conjectures. Okay. Okay. Now, also, we have the Gonadi conjecture, and Gonadi is just simply say the following thing. You take a sufficiently large degree embedding under some very line bundle L, then you look at its minimal resolution, just like what we did before. And then instead of Griffith index, then the question is then the shape of the minimal free resolution should tell you the Gonadi of the curve. That is what the Gonadi conjecture said. Let me just skip some of these details. And now, basically, you look at the dual of this resolution. What happened? Then the module you resolve is this RC, KC, comma L, which is a direct sum of KC tensor LM. Yeah. And this guy here. Yeah. So this is linked back to the canonical line bundle of the curve. And from that, it's not too surprising them. This should tell you a little bit about the Gonadi of the curve. And that turned out to be indeed the case. And so this is done by Lysa and I did a few years, almost 10 years now, that saying that this Gonadi conjecture is true. And the proof is that you reduce the calculation to symmetric product of curves, just like basically the observation due to Voisin. What Voisin did is using Hilbert's scheme of points on the K-free surface, but Hilbert's scheme of points on the curve, you just get a symmetric product. And you see the question is pretty reasonable. If you have a curve, then what is the geometry of the curve? Then basically the geometry of subvariety, yeah. But the subvariety of C are precisely points. So, and the marginalized space of D point on C is just simply the symmetric product of the curve. And basically, Voisin observation is that one can reduce the calculation on some of the Cousin group calculation or the Syzygies calculation, reduce it to question about vector bundle on the symmetric product. And this is roughly the idea of the proof of this so-called Gonadi conjectures. Now, maybe in the last few minutes, let me talk about higher dimension a little bit. And here, one can talk about so-called asymptotic syzygy. So the setup is something like this: LD but equal DA plus P. But if you want to just think about the case of L equal to DA, and RD is the number section, is the number section of this line bundle, and you form if B is any other divisor on X, you can form this called abstract module RBLD. And now we want to compute the Cousin homology of the syzygy of this thing when D is sufficiently large. And by regularity and things like that, one get a lot of vanishing theorem. And now, what happened? So the length of the resolution is RD, and RD basically is like big O of D to the n. So the length of the resolution is very long. So in things like NP property, usually is only work for the first few terms, and it's basically linear with respect to D. And so you somehow ignoring a lot of information of what happened in between. And what this theorem is essentially saying that, yes, one can do this. And in fact, most of this group is non-zero in the possible non-zero range. And the basically is this see here. So it's here. This tells you that where it is the range where it's non-vanishing. So we proved that most of the terms are non-vanishing. But what we don't know was that whether this is asymptotic sharp. And Park was able to prove that 1 or 2 years ago, that in fact that this is the case. And he proved that in fact you get the vanishing in this range as we predicted. And the proof is very nice. And again, one can reduce essentially to product of projective space by the work of Reiku. And let me just explain a little bit what happened in the projective space case. In the projective space case, turned out that this is look like a little bit like the curve. I mean, his induction, instead of think of Pn and then you look at the hyperplane Pn minus 1, his induction is think of Pn as the n-symmetric product of P1. Yeah. And then you're relating the Hilbert scheme of length n scheme with the length n minus 1 scheme, and by instance correspondence, basically the so-called flat Hilbert scheme, and or the equivalent in this case is the universal scheme of length n. And turn out that again by studying vector bundle on this basis, one is able to prove the vanishing theorem, and therefore that would be enough to prove that the conjecture that we made about asymptotic vanishing. Now, our knowledge about these things are pretty minimal in some sense. I mean, even for the simple thing like the Varieties variety, there we have proved some very precise non-vanishing theorem. And the method we use, one is using monomial ideal and reduce the question to something of length 0 scheme. The other one is using cohomology class of subvarieties. And the surprising thing is that these two very different methods somehow lead to the same bar. And so this leads us, myself and Leisnerfeld, feel that maybe we can be super optimistic and maybe this bar is already sharp. For the case that when the D equal to 2, that for this quadratic Varieties embedding, at least in capital 0, and there's work of Wayman and his co-worker that in fact show that this is indeed the case, that the non-vanishing theorem is good, at least in capital 0, that this is the bar. And all right. So, but for instance, there are questions like the size of the Gaussian group, and one can, together with Ehrman, we make some sort of guess that just like the case of curves, you can see that sort of the Betti table. So if you fix, it's sort of like it's normally distributed. I mean, if you graph them, they sort of look like a bell curve. And one can ask whether this may be true in general or not. But again, knowledge about this kind of question is minimal. And some of the other topic I probably should have included is probably like the work of on Boy-Soderberg. And this is a theory about the possible Betti table in totality. basically one can so look at the Betty table of projected Cohen-Macaulay variety. After by cutting by hyperplane, you reduce it in terms of zero-dimensional scheme and on the R1 n space. And now, anyways, there's some really beautiful work of Eisenberg and Stryer talk about the convex cone generated by this Betty table, and they sort of describe this convex cone and saying that the extremal rate are precisely the so-called pure resolutions. And other thing I should mention maybe is like the work of Farkas, Kemeny, and Ascotini that on the secant conjecture of Green and Lysenfeld, which is a refinement of the Green's theorem saying that 2G plus 1 plus P satisfy NP. But now, roughly speaking, you can look at 2G plus 1 plus P minus C, where C is the Griffith index. And then assume L is very ample, and then you can ask whether the thing is satisfied NP or not. And again, for genetic curve, this is done by Farkas and Kemeny, and then for Griffith index, small Griffith index, and this is also some recent work of Agostini, and that's some very nice work linked back to the work of Poisson and also some of our work on Granati conjectures. And then there's also the monomial ideal that is given by Stanley Risner and is related to combinatorics. And then there's also the genetic initial ideals and Grobner basis, etc. And then also somehow something between curve and high dimension, that would be the work on the secant variety. That somehow this is the joint work with Rambo, Neal, and Park. Again, anyway, maybe let me just stop here.